Welcome to third seminar in EMC web seminar series. Today we'll discuss what is EFT. And with any acronym, the first thing we need to do is define or clarify what's an acronym. So here we are talking about electrical fast transients. As the name suggests, it is one kind of noise signal that is fast in nature. And if you look at the definition, it's a burst of interference pulses that simulates inductively loaded switches. It sounds complicated, but it isn't. Let us look at a simple example of a power drill. The electrical motor in most simple power drill is an inductive load. When you run your power drill, it generates lots of noise on power lines. Any other equipment on the same power line will be subject to that noise. If you have your freezer in your garage and if you operate your power drill next to it, you want your freezer to get affected by the noise generated by power drill. If your compressor starts acting weirdly or it starts switching, if your display blinks, are you going to keep it at the freezer? If answer is no, that's the reason why appliance industry cares about EFT. But appliance industry is not the only industry that cares about EFT or electrical fast transients. If you look at an industrial environment, it's even worse than the home environment. You will have a huge noise generated by big motors. And that's why you will see that there are lots of industries that requires that you perform an electrical fast transient testing on your system. Now, how you do that testing? You cannot use like a power drill from XYZ manufacturer to do the testing. You need definitely a much more defined and controlled setup that you can use to reliably repeat results every time. The International Electrotechnical Commission, or IEC, has defined one such standard to address this concern. It's a system-level standard that defines test voltage waveform, range of test levels, a type of test equipment you should use, test setup, and test procedure. First, let us look at test waveform. There are a few interesting things in a test waveform. First thing, as you can see, is you see a multiple small pulses, and there is some on time, and then there is off time. As per the spec, there will be a 15 milliseconds of on time where you will have multiple pulses, and then the whole signal repeats after 300 milliseconds. So actually you have a 285 milliseconds of off time. And that way, actually, the figure is not to the scale. It doesn't seem that you have enough off time, but actually off time is much bigger than the on time. Now, suppose if you try to look at or analyze one of the pulses, all the pulses look same. It may look something like this. Now, if you look at the scale, one is an X scale. An x-axis is a time, y-axis is amplitude or voltage. You can see rise time is just a 5 nanosecond, and the pulse width is only 50 nanosecond. And this amplitude can be in a kilovolts depending on the test level, and also the frequency that also depends on the test level. The frequency is again a repetitive time between your pulses. Let us look at test levels. IC 61000-4-4 defines 4 test levels. So let us look at say level 4 as an example. Since for level 4 your peak voltage is 4 kilovolt. So if you look at the previous slide, this peak amplitude can be 4 kilowatt if you are using a level 4 requirement. Then the repetition rate is 2.5 kilohertz. This is the burst frequency, this repetition rate. Now, when we are doing this testing, depending on where you apply the noise, there are two separate levels or voltage levels. First is you do your testing, mainly testing on a power supply ports. So if you inject this noise on line and neutral, then you need to use the 4 kilowatt peak level. But the same noise can be given to an IO signal data or control ports. And for this testing, you need to use a different kind of test setup that we'll see in upcoming slide. But in that case, the peak voltage reduces to 2 kilowatt rather than 4 kilowatt. And repetition frequency is 5 kilohertz instead of 2.5 kilohertz. And different levels, depending on the levels, the peak amplitude will change. Now, as you see, there are 4 levels. So now, which level should you use for your testing? So if you have a well-protected environment, then you should use a level 1 testing. The question, you may ask a question, what is a well-protected environment? The installation is characterized by the following attributes: a suppression of all EFT bursts in the switched power supply and control circuits. There is a separation between power supply lines AC and DC, and control and measurement circuits coming from other environments belonging to high severity levels. There is shielded power supply cables with the screens earthen at both ends. Like maybe the computer room may be a representative of this environment. The next one is protected environment. In this case, the installation is characterized by the following attributes: a partial suppression of EFT or burst in the power supply and control circuits, separation of all the circuits from other circuits associated with the environment of higher severity levels, a physical separation of unshielded power supply and control cables. Maybe the control room or terminal room of industrial and electrical plants may represent this environment. Third is a typical industrial environment where you may have no suppression of EFT or burst in the power supply and control circuits, or which are switched only by relays, no contactors. There is a poor separation of the industrial circuits from other circuits. There is a dedicated cables for power supply, control signal and communication lines. There is a poor separation between power supply, control signal and communication cables. Most of the area of industrial process equipments and the power plants and relay room of open air will fall under this category. And fourth one is a severe industrial environment. And the installation is considered like a no suppression of EFT or burst in the power supply and control circuitry, no separation of industrial circuits from other circuits, no separation between power supply and control signal and communication cables, and use of multi-core cables in common for control and signal lines. This is one of the worst environments the outdoor area of industrial process equipment may fall in this category. Now, as per my experience, I think most of the customers, they either go for level 3 or level 4 compliance. That's the typical trend I have seen in the various industries. Now, if you look at the waveform, the burst polarity can be positive or negative. Means you can have a positive going pulse, or you can have negative going pulse, but only one at a time. You cannot have both positive or negative going pulse. This pulse can be an asynchronous to power supply. It may not be synchronized with, it always occurs at a 0 cross of a 50 Hz signal or 60 Hz signal. It can be asynchronous to power supply. Now for testing purposes, there may be a various coupling modes, because in real world you cannot guarantee that you will only have a noise on line or neutral or on earth. So for that purpose there are various coupling modes. For power supply testings, you need to have, say, one is an internal where you may have a line, neutral, or power earth, or combination of all these three. So you can have a combination that you may have a common mode noise between line and neutral, or line and earth, or you may have a common mode noise across line, neutral, and power and earth. There are lots of coupling modes, and you need to check all the modes, because in the real world you cannot guarantee that you will have only certain kind of noise or transients. The second coupling mode is I/O and communication ports. For this kind of testing, you need to use a capacitive coupler. We'll see it in upcoming slide. So now the next question is how you test it. So first, this slide explains how you check a power supply ports. In this case, what we have is we have an equipment under test that we are trying to verify. We want to see the behavior of this equipment in case of electrical transients. You need to have an earth plane, a conductive plane. You need to have an insulating material where you need to put your equipment. Now this equipment generates a fast transients or burst, and this equipment typically tends to have two separate inputs. One, that's an instrument mains input or instrument power input that is used to operate this equipment, and second one is the equipment under test mains input. The advantage of this configuration is that you may have this equipment that's supposedly designed to operate at 110 volt. But you want to check a 230 volt equipment that you have designed for other countries. And what you can do is if you give a 230 volt input here, the equipment injects a noise over the 230 volt signal, and that goes to your equipment. That way you can use the same equipment for both 110 and 230 volt testing. And that's very helpful for many manufacturers who supplies in various countries. Another thing is many customers, they put a power conditioner at this point that E to mains input to the EFT bus generator. The reason behind that is they want to make sure they are giving a good power to the equipment, and then they are generating real EFT waveform that's specified by IC. They are not creating even situation worse than that, because many customers may be operating in their industrial environment, and that itself the power line is not that clear. The next test setup is for actually data I/O lines. In this case, suggested one needs to use a capacitive coupler. So what happens is all the cables in equipment are passed through this one capacitive coupler. It's a metal object that is 1 meter long, and there is two opposite metal lines, and you pass your cables from in between, and that way you are capacitively coupling a noise into wires. And then this capacitive coupler is connected to the EFT test generator. Rest of the setup is same, where you have insulating material as well as the earth plane, your equipment under test. And in this case, we are injecting noise into data I/O lines, and we are trying to verify the noise effect or transient effect. So if your cable picks up the noise, what happens? So now, how you address all the EFT issues? Now, if you look at the EFT, there are two possible coupling modes. One comes from a power supply, so where you have a noise on your line and neutral, and the second one is on data I/O lines. So some of the easiest fix is you put a line filters at the input of your system, And that way they will try to block a noise or transients that are coming through a line or neutral, and that way your circuit may not see that noise on the line and neutral. Another possible thing is you use a transient protectors or use an isolation transformer. Particularly, suppose if you use ferrite iron core transformers, then most of the time you may not have any issues with the electrical fast transients, because those big transformers acts as a filter. They cannot transfer this high frequency signal. They just pass a 50 Hz signal, but they will definitely block such a high frequency signal, and that way it itself acts as a filter to remove all the noise. Then another thing is you may have, say, use a voltage regulators and other good power supply design to take care of the noise. And because of this, what happens if the worst case for electrical fast transients are the system where you use a transformer as power supply. In that case, you may not have voltage regulators, isolation transformers, so whatever noise is there on the power lines, it directly comes into the system. One more fix for this is to use isolated high power circuitry. So if you use opto isolation between your low level digital logic circuitry and high power circuitry, that again helps, because digital circuitry or sensitive components are not seeing those high frequency power circuitry directly. In seminar 2, we looked at an ESD, or electrostatic discharge. So now let us try to compare an electrostatic discharge event and EFT and how they stand against each other. So first is, if you look at the maximum voltage, in case of ESD, if you use an air discharge, maximum voltage is 15 kilovolt for level 4, otherwise it's 8K. In case of electrical fast transients, it's just 4 kilovolts. Its peak amplitude is much lesser than ESD. But if you compare energy, in case of ESD event, energy is less than 10 millijoule, while in case of EFT, energy tends to be around 300 millijoule. It's much higher. In case of ESD, if you look at a repetition rate, most of the time it's just a single impulse, while in case of EFT, we have multiple pulses. They are repeated at 5 kHz for level 1, 2, and 3, and for level 4 power supply, it's 2.5 kHz. Now the spectrum, ESD event has a rise time of 0.7 to 1 nanosecond. That results in a spectrum of almost 1 gigahertz, while EFT has a rise time of about 5 nanoseconds, and that tends to result in a spectrum of 100 to 200 megahertz. Now if you look at the spectrum itself, you can see that this tends to be much higher than the typical frequency your embedded system runs at. And therefore, many times you need to think like an RF designer to fix these issues rather than having a mindset of an embedded designer. So this was a basic comparison between ESD and EFT. For this particular class, we refer to an IEC 61000-4-4 specification. You can buy the spec from IEC website. And this ends the third web seminar, What is EFT? Again, please give feedback and help us in improving the EMC web seminars. Thank you.